Okay, welcome back to our second and final set of notes on Chapter 7. We left off with this diagram here with the laser, but we didn't really talk about it a whole lot. This is basically an application of wavelength, which is something we've talked a lot about so far. Basically the way a laser works is you get this reflecting mirror and a lamp that runs along the outside of it. And as that lamp glows, it emits a wavelength. And the way a laser is designed is that as that wavelength is continually emitted down the length of the laser, the wavelengths are exactly the same, so that the peak of one wavelength matches the peak of another, and the trough of one wavelength matches the trough of another. And so when two wavelengths are in sync, they actually make the wave more intense. And so then as we put more and more waves in sync, our product is much more intense than we would be able to make with just a single glow. So what we get at the very end is the cumulative effect of all these wavelengths being in sync is a really, really, really bright light. So that's kind of an application of wavelength for chemistry. So that's laser light. So electron microscopy here is another application to wavelengths. When you use a regular light microscope, your wavelengths are rather long, so you get, when you look at something that's very, very small, your wavelengths will become kind of blurry and you won't get a great image. But when we use an electron microscope, our wavelengths are so small that we can get really, really, really crisp images on super small things. And so here's an electron microscope with its wavelength at 0.004 nanometers, super small, and they can tell the differences in these cells, the sickle cell and the normal red blood cell. And here's scanning transmission microscope, or scanning microscope of iron atoms on a copper surface. And so here they can even kind of get an idea of the shape of atoms because they're using electrons with their super small wavelengths. So, talk about the Schrödinger wave equation. Schrödinger-Roden equation, 1926, described both the particle and wave nature of the electron. Up until this point, we had Bohr's idea that electrons existed in certain energy levels, and we saw that a little bit with our light that we talked about in class there. But Schrödinger wrote one with the wave function. And wave function is going to describe a few things. The energy of an electron with the given wave function and the probability of finding that electron in any volume of space. So Schrödinger's equation can only be solved exactly for a hydrogen atom. It's kind of like Bohr's. We started with the hydrogen atom, and we have to approximate its solution for multi-electron systems, which would be everything else on the periodic table. So here's what it is. If you took Gen Chem, a lot of this stuff is going to sound familiar. But the wave function is a function of four numbers called quantum numbers: n, l, m sub l, m sub s. N is the principal quantum number. They're 1, 2, 3, 4, on and on to 7. That's the distance of the electron from the nucleus. So you remember things like 1s2, 2s2, 3p6, that kind of stuff. Those 1s and 2s and 3s, those are n's, the distance from the nucleus. And so here you see the kind of a space filling diagram of 1s orbital or shell is pretty small, and then 2s is larger and 3s is larger, on and on it goes. So that'd be n equals 1, n equals 2, n equals 3 respectively. So for n, that's going to be about 90% of electron densities found for 1s orbital is looking like it's about a sphere. We can't know the exact location and the exact velocity of an electron, but it's pretty safe bet that somewhere in this circle, if an electron were to pause and let us, take a picture of it or something, it'd probably be within this darker green area. And so here's a graph for radial probability and distance from the nucleus. As you get further from the nucleus, the chance of the electron being out here perhaps, is very, very exceedingly rare. So it takes us to L. L is angular momentum, and angular momentum, we've got L as 0, 1, 2, 3, on and on, but L is always equal to n minus 1. And so if n was 1, if you were in 1s2, your angular momentum would be 0. 1 minus 1 is 0. If your n is 2, you're in the 2s2 or 2p6, something like that, then your L could be either 0 or it could be 1. And if n is 3, then L could be 0, it could be 1, or it could be 2. And so If L is 0, it's an s orbital. That's how we get 1s. If L is 1, it's a p orbital. If L is 2, it's a d orbital. And if L is 3, it's an f orbital. So it gives us an idea of our shapes that we're going to get for our regions of probability that we're going to find an electron. And so the L, the angular momentum quantum number, basically tells us the shape of the volume of space that we're going to find this electron in. And so S is like a sphere. It's just pretty much going to be a circle if L equals 0. If L equals 1, it'll be a p orbital. This is generally described as dumbbell shaped. It does exist three-dimensionally, and so it could be a dumbbell going along the x-axis, a dumbbell along the y-axis, or a dumbbell along the z-axis, any of these locations. The further we get, the more complicated it gets. D can look like any of these shapes, again in three-dimensional space. And so then we get to magnetic quantum numbers. That's m sub L. For a given value of L, m could be -1, 0, or +1. If L equals 1, a p orbital, we could be -1, 0, +1. And if L equals 2 in a d orbital, we could be -2, or we could be -1, we could be 0, 1, or we could be 2. And that's going to tell us how this orbital is oriented in space, because like I said, we could be along the x-axis. On something simple, we could be the x-axis, the y-axis, the z, or we could be here. You have not only multiple axes to be on multiple shapes. So that's how you get this kind of idea. So here's your three orientations in space. Going along the x could be -1, going along the y could be 0, going along the z could be 1. So that tells us how we're oriented in 3D space. Now if we make it a little bit more complicated, we get 5 orientations in space. And so this is why we have to have 5 numbers, a -2, a -1, a 0, a 1, and a 2. A -2, a -1, a 0, a 1, a 2, because there's different orientations and there's different shapes with this kind of dumbbell with a donut around it idea. So that takes us to ms. That's a spin quantum number, and the spin is pretty easy. It's a +1/2 or a -1/2. If it's spinning one direction, that's a plus. If it's spinning the other direction, that's a minus. We denote these with up arrows and down arrows. You probably remember filling those out to get to describing these things in Gen Chem, where we had to say it's 1s2, 2s2, 2p6, 3s2. You had to fill them in with an up arrow and a down arrow and continue on with that manner. And you might have done that a little bit in physical science too. So here's your idea of an oven firing a beam through a slit screen. It passes through a magnet, and then as it passes through the magnet, the positively charged are going to go one way, the negatively charged are going to go another way. So that lets us know that there are electrons with different magnetic orientations. So now, the existence and the energy of an electron in an atom is described by its unique wave function. Every electron has its own unique wave function. So the Pauli exclusion principle, no two electrons in an atom can have the same 4 quantum numbers. So if you're telling me that one atom exists in the 1s orbital and it's the upspin atom, then no other electrons can be in the 1s orbital with the upspin. They'd have to have a downspin or be different. They can't have the exact same numbers. You can kind of think of it like an address. If the 4 numbers that make up the wave function make up your address, then there can't be, multiple families or multiple houses living at your one address, because we wouldn't know where to find people. So each set is uniquely identified. Here they give the example of maybe stadium seating, perhaps, being a set of numbers that guides you to the location for just you. An electron, the Pauli exclusion principle, is a set of numbers that guides us just to that one electron. And so here they are: N, 1 through 7, L, n-1, magnetic quantum numbers, zeros, -1s, -2s, 2s, and then the number of orbitals that they'll each hold. And the number of orbitals tells us how many electrons we can hold. And so we call a shell these electrons that have the same value of n. If you're 1, 2, 3, 4, you're in the same electron shell. Subshells have the same values of n and l. And then an orbital, if you have the same values of n, l, and m, then you're in the same electron orbital. So how many electrons can an orbital hold? It can hold 2. If n, nl, and m are fixed, then the only thing we can change with our electrons are whether they're a positive 1/2 or a negative 1/2. And so our wave function is going to be, you're in this energy level, you have this L, you have this M, and you're a positive 1/2, or you're in this energy level with this L, this M, and a negative 1/2. So each orbital can hold 2 electrons. So how many 2p orbitals are there in an atom? If your n is 2 and your p would have to be L, which is n minus 1, would be 1. Then if L is 1, then your magnetic number could be a negative 1, 0, or a positive 1. And so that means there's 3 orbitals here, and it can hold 6 electrons. The 3 orbitals are its 3 different orientations in space, and it could hold 3 orbitals, 6 electrons. How many electrons can be placed in a 3D subshell? That would be n equals 3, L equals 2 because it's 3 minus 1. And if L equals 2, then our magnetic number would be negative 2, negative 1, 0, plus 1, or plus 2. So there's 5 orbitals, and those 5 orbitals can hold a total of 10 electrons. And so hopefully you recall, this is a little while back, but hopefully you recall we had to memorize in Gen Chem that an s orbital could hold 2, a p orbital can hold 6, a d orbital can hold 10, I might run out of room here, and an f orbital can hold 14. So I had you commit those to memory when you were in Gen Chem, SP, D, F in that order, 2, 6, 10, 14. If you don't know, start with 2, add 4 each time, that's where you end up. And those are the number of electrons that each can hold. And so that kind of explains this whole 2p6 thing. 2 is the principal energy level, and then p holds these 3 orbitals. Each orbital can hold 2, so you're going to be maxed out at 6. If you get more than 6, then you need to go to the d or s or whichever is next from where you are filling these, and continue to go on with your electrons from there. So you might want to commit those to memory. They'll be helpful later. Okay, so if you look at energy of orbitals in a single atom, energy only depends on the principal quantum number n, which would just be 1, 2, 3, or 4. But of course, most atoms have more than 1 electron, so this doesn't become useful for very long. But here your energy would be equal to your Rydberg constant multiplied by 1 over n squared, n being your principal quantum number. So there's the first energy level at the bottom, second energy level at the top, 3, 4, on and on it goes. Now, here's something a little more realistic. Multi-electron atoms, energy depends on n and l, so not just your principal energy level, but also 2s and 2p are going to have different energies, and sp and ds and f's and s's are all going to have different energies. So here it shows you how the L is 1 here as opposed to back here where L is 0, how that changes the energy of those electrons. So that's about all we need to know there. What you need to know for Aufbau principle is you fill up electrons in the lowest energy orbitals. So first you go to 1s2, and then you go to 2s2, 2p6, and when those are full you go to 3s, and then when that's full you go to 3p, and then when that's full you note that you don't go to 3d. You go to 4s, that's the next lowest energy. And I'll show you a diagram later that's a bit easier than this to use. But you go to the lowest energy first before you go to higher energies. So hydrogen has 1 electron, you just draw 1 up arrow. And then that would be it. So hydrogen, you could describe its location as 1s1. We know that electrons in 1 is its principal energy level, it's in an s orbital, and there's 1 electron there. That tells us a lot about that electron. Now helium has 2. And so we said S can hold 2, so you would draw 1 down arrow. 1 up, 1 down is helium, and you'd call that 1s2. Lithium has 3, so now we got to jump up to 2s. And so you describe lithium as 1s2, 2s1. Beryllium has 4, so you'd do the other down arrow. You'd have 1s2, 2s2. Boron has 5, so you draw 1 up arrow in the 2p, so you'd have 1s2, 2s2, 2p1, and you can go on and on and on and on like this for the whole periodic table if you want, except for this. You shouldn't do that. That's bad. You should go up arrow, up arrow, up arrow, down arrow, down arrow, down arrow. So they're just doing that to mess with you. You don't want that. You want that. That's the way to do it. So the most stable arrangement of electrons in a subshell is one that has the greatest number of parallel spins. That's Hund's rule. And so parallel spins is the up arrow, up arrow, up arrow. And then you backfill with your downs. So carbon has 6. It would look like this. It would be 1s2.